All right, so I can see from the first derivative graph, which is given to us, that at -2 I must have a local max, because the derivative changes from positive to negative, and at 0 I must have a local min, because the derivative changes from negative to positive. At x equal 2, the derivative doesn't exist, but it's not a max or a min. And I did not mark this point, so I'll just give you the name right now. And f of 3 must be a max as well. So then you know that if the derivative graph is above the x-axis, then f is increasing, and if the derivative is below, then the function is decreasing. And so when the graph is concave up, is when the derivative graph is increasing, so that's -infinity to -2, -2 to 2, and 6 to infinity. And then when f is concave down is when this graph is decreasing, and so that's just from 2 to 6. So putting all these pieces together, so I've got a local max here, it's kept up, and then it comes down, and then at 2, I must have a vertical tangent where the derivative doesn't exist. And then it's up here at 3, must be a maximum. And then it changes concavity, but it keeps going down when I get to x equals 6. All right, so this one here, I need to make a number line, and it's 0 and 5 are the two critical numbers, so I need to check numbers in between. So if I look at f prime of -1, I get a positive number. So that means the function is increasing. If I check 1, I also get a positive number, so it's still increasing. And if I check a number like 6, I get a negative number. So that must mean there is a maximum at f of 5, because y prime changes from positive to negative. So necessary to say that if you're using the first derivative test. All right, oh, I didn't get the graph on this yet. All right, let's get this graph going. This crosses through 0 on your paper. All right, so this was the point -4 and -2. So from this, I can find out what the critical numbers are. And they have to be the right kind of critical numbers to use this second derivative test. And they're the kind of critical numbers where the derivative equals 0. So I get two critical numbers, -4 and 0. So this is the y prime graph. So it is necessary that I draw the second derivative graph. So at the point -2, I can see the slope is 0. So that must mean it crosses here at -2. And then at the point 4, on your paper it's marked, the point 4, its slope is 0, so it crosses here at 4. So it's negative before -2, so it's decreasing, and then it's increasing, so it's above the x-axis, and then it's decreasing. All right, so this must mean that, and now I want to use the second derivative test, so I'm looking for the sign, the y value of what the at x equal -4, so that's back here, so it is negative, so that must mean that I have at -4 a local max. And then I need to go, this is the point 4, then I need to go and check the point at x equal, the second derivative at the point x equals 0, and that is positive, so therefore it's kept up, so I must have a local min at that point. All right, moving on to the new material. Okay, so this I can see, I'm going to let u equal the denominator, and du is 7dx. So I can take that 2 on the outside. That can be a helpful thing. Oops. So 7x plus 3 dx. So to get rid of dx, I'm going to take this and to multiply both sides by 1/7. So I get 2, 1 over u, du, over 7, so I can take the time to take that 7 on the outside, so I just have 1 over u. So 2 over 7 gives me ln of u, and then put the u back in. Okay, so moving in, I'm going to use this as my u, this inside e. So du is e to the x dx. So I'm going to rewrite this, because I'm going to use this for my u, and then I also have this other e to the x dx. But that's what I needed to take out to put in my du. So I get secant squared of u, and I know that's tangent of u, and then I put the x's back in. All right, next one, I know the inside of the fourth root. I'm going to let that be u. And you know what the derivative is. That's negative cosecant squared. And that's what you have sitting right there. So let's just rewrite it so we can clearly see it. So cosecant squared x dx. So this can come out. I almost have it here, so just do the little alteration of moving the negative sign. So negative du goes in for cosecant squared, and then I have u to the 1/4 power. I'm just going to write it that way. So then I'm going to pull the negative outside, and I'm ready to integrate. So I get 4/5 u to the 5/4 plus c. And you don't have to worry about carrying the negative sign through to the c. So negative 4/5, and then put the x's back in to the 5/4 plus c. All right, here I'm going to let the u equal the inside x squared function. So again, looking at what I've got, cosecant x squared, cotangent x squared, x dx left over. So I see x dx. So I'm going to alter this by dividing through by 2. So I'm going to say I've got cosecant of u, cotangent of u, and I replace dx with 1/2 du. Pull the 1/2 outside, and thinking about the antiderivative of cosecant cotangent, I get negative cosecant of u, and then I put the x's back in. Okay. So here I get to this inside function, this 5 to the x is in the inside of the cosecant squared. So I'm going to let u equal 5 to the x, and you've got to know the derivative is times ln of 5. So let's rewrite this. So I see what I've got left over here, 5 to the x dx. I know ln of 5 is a number, so I'm going to divide both sides by that. So this comes out, and I get 1 over ln of 5 du in its place, and I get cosecant squared of u. So definitely take the time to pull that on the outside, and then you see it, negative cotangent of u, and then put the x's back in. 5 to the x plus c. All right, last one here. I'm going to let u equal the denominator. And the du will give me e to the x dx. And then rewriting this, I can see that this is necessary to take out to get my du in there. And this underneath, in the denominator, I get 1 over u. And there it is, our friend ln. And this is 1. I'm starting to write it. This is 1. This is always positive, so it could be rewritten as e to the x plus pi with parentheses if you choose.